All right, so we are back for lecture number 2, I think. This is what this will be. And just as a quick review, right, just to kind of catch everyone back up in case the ordering kind of changes. So last time we had finished and we had discussed about ethers and some of the different methods that we have for making ethers. If you look in the textbook, there are a couple of other reactions here and there. Especially on, let's see, it was page, where was it? Right there. So section 13.6, right? Section 13.6. Talks about a couple things. It talks about the reaction of ethers with acids, which is pretty important, okay? And then it also talks about oxidation, which not that important. But definitely take a look through that stuff about the acids there. It's pretty simple. You guys can figure it out, I think, without me kind of walking you through that. But take a look at section 13.6. Definitely something to consider, okay? All right. So anyway, let's move on from there. And the next thing we want to talk about is epoxides, okay? So epoxides are a type of ether. All right, so what we need to realize then is that the reactivity that is present with ethers is present in epoxides for the most part. Right, we'll touch a little bit about the reactivity that's talked about in section 13.6, and so you'll see I'm kind of lumping those two together there. But if something doesn't make sense, go back and check that out. But anyway, so an epoxide is a cyclical ether. Okay. So if we have, and there's a couple different forms of this, the simplest being that guy right there, right? So we have a three-membered ring, right? A three-membered ring where one of the points of the triangle is an oxygen, right? I was trying to come up with a clever way of saying that, right? But we've basically got a cyclopropane, except one of the carbons is replaced with an oxygen. And so if we go back to our organic 1 discussion where we first introduced this idea of cyclical compounds, right? There is something that we have to take into account: ring strain, right? If we take a look at a three-membered ring system, we've got the bond angles in there that are not anywhere near the ideal, tetrahedrals, right? 109.5, right? They're nowhere near that, right? They're closer to 60, 70-ish maybe if we're lucky, right? But so there's a lot of ring strain in there. So epoxides are going to typically ring open is what it is, right? So we're going to do ring opening reactions with epoxides. Something's going to come along and they're going to cause that three-membered ring to open up one way or the other, okay? There are 4 and 5 and 6-membered rings also, which are technically called epoxides, although what exactly is the definition of an epoxide and all this kind of stuff kind of varies depending on what we want to look at, right? But the broad definition is an epoxide is a ring that contains an oxygen inside of it, right? So we can have cyclobutane, right, a square, right? We can have a 5-membered ring, right, and we can even have a 6-membered ring. Okay. In general, right? In general, these will behave like ethers, especially as you get out to the 6-membered rings, the more stable rings right there. The 5-membered ring is a particularly useful ether, tetrahydrofuran, THF. You'll end up seeing that one quite a bit as a solvent and as a as a reagent, not a reagent, or well, it's kind of, I guess, a reagent in some Grignard reactions and things like that. But that's a little bit of a different conversation if we were teaching the majors organic chemistry course, okay? So technically, any type of ring system with an oxygen, we're dealing with an epoxide in there. By far, what we refer to really, especially in OChem, is dealing with the 3-membered ring there, okay? So let's talk about how to make an epoxide and how to kind of react and do some cool stuff with it, okay? So again, there's the naming part that's in the book there. Go through, read through that, kind of interesting, and then. But as I mentioned in my previous video, naming is something that's systematic, right? So you just read through the rules and follow the rules, right? So not something I'm going to spend too much time discussing in the video lectures here. All right, so question, how do we make an epoxide, right? Now, the most common way, and really I guess the only way that we're gonna learn, off the top of my head, I can't think of another way that we're gonna learn how to make epoxides for this course. So maybe I'll prove myself wrong somewhat later in the semester, but for the moment, you gotta start with an alkene, okay? So we'll come back to this in just a second, but we gotta remember then how to make an alkene to begin with, okay? But starting with an alkene, we can turn an alkene into an epoxide, okay? So here's what we want to do, okay? So turn the alkene into an epoxide there. And to do that, there are two methods, okay? Let's talk about the simplest method then. Okay? So the simplest method is we put in some McPubba. All right, okay, I'm being dumb, right? MCPBA, right? So what in the world is that? So MCPBA is a very common reagent in organic chemistry. All right, so that is what MCPBA is. In probably just a couple lectures, we'll start to get into aromatic compounds, and we'll talk about the naming, nomenclature with aromatic compounds is going to be pretty darn important. So I'll spend a little bit more time there. But the lowercase m stands for meta. Meta just stands for or refers to where on the ring things are attached. Okay, so don't worry about that too much now. Just meta means they're in a 1 and a 3 position, right? So if you want to think about it real quick, 1 and 3. Okay, so metachloroperoxybenzoic acid, right? So peroxybenzoic acid is this, or a peroxy acid is this group here, and it's attached to a benzene ring, okay? So what in the world is a peroxy? So if you think about it, okay, if I ask you guys to go back to when life was simpler, okay, when life was simpler in Gen Chem, right, we learned how to name things like this. And we called this hydrogen peroxide. A peroxide is where we have an oxygen bound to another oxygen through a single bond, right? This is a peroxide group. It is a peroxy acid, and it is attached to a benzene ring, right? So peroxybenzoic acid is what it is, okay? So hydrogen peroxide, right? Peroxybenzoic acid here. Okay, so same kind of idea there, all right? Why do we use it? What's the purpose? What's the point? Well, the thing is, we can do this exact same reaction with pretty much any peroxide, okay? And in fact, there's some common organic chemistry labs where you take hydrogen peroxide and you can use that to make an epoxide and all this kind of stuff with it, right? The benefit, and this is something we don't talk about too much, it's not really emphasized in the book, and we mention it a lot in the lab, or as much as we reasonably can. If you want to think about it, right, if you take a look at your starting material here, if you try to run this reaction in hydrogen peroxide's in an aqueous solution, right? That stuff's not going to be soluble in an aqueous solution. And to get the reaction to happen, we have to add some kind of phase, transfer agent then to make one homogeneous solution, and then it can hopefully go on and do what it needs to do, right? That kind of thing. But anyway, this right here, the MCPBA, is soluble in most organic solvents. So if we wanted to pick a solvent here, like, I don't know, dichloromethane or whatever you wanted to do this in, right? This will be soluble in there, and then it would go through and run the reaction, okay? So this is by far the reagent of choice to make a peroxy acid. This is also used in some cases to do oxidations, okay? So this is any peroxide is a good oxidizing agent. Now you guys already knew that, right? And if you're like, what in the world is an oxidizing agent? How does he know, right? All this kind. So remember, an oxidizing agent, we're basically just adding oxygens to an organic molecule, okay? So go back and take a look in your OChem 1 notes, and you can find instances where we use peroxides to do oxidizing chemistry already. Okay, but anyway, so good choice there to make an epoxide. Okay, The other option, let me just make some space right here. All right. The other option is we are starting with alkene again. And this is going to be a two-part reaction, and then we'll bring it together. Okay. There's part number one. Interesting. Br2 in water. So, what in the world does this reaction do? Well, this is a good time for you guys to pause, and I'll tell you that this is an OChem 1 reaction. So, do you remember what this does? Okay. Do you guys remember the mechanism for this one? Right. That's also important. That's something you guys should know, right? So can you guys draw the mechanism? Can you guys remember the reaction of what happens when you have an alkene and you do a halohydrin reaction? So halohydrin is what that is, right? And at the end of the day, right, if you guys have paused and you went through that, or if you did it all in your mind, right? What happens is we end up adding an alcohol and a bromine. Okay. Now, which one gets added to the more substituted side, which one gets added to the less substituted side, and what's the mechanism and all that kind of stuff. Very important to know, okay? Why did I draw one wedge and one dash, right? Does it make enantiomers, all that kind of stuff? The answer is yes, right? There's a lot that goes behind this, and that's what I need you to get when I'm asking you guys to pause and think and work through this. That's what I'm asking you guys to do, okay? So please, please, please go through and think about that kind of stuff. As I said, if I had infinite time and infinite space, then I would sit here and spend hours and hours and hours recording all this stuff for you guys, but I don't. So I'm relying on you guys to, to work through that stuff. And please don't hesitate to, contact me, and if you have any questions, just let me know, okay? I'll try and help you guys as much as I can, I promise, right? So anyway, we end up generating that reaction there, or excuse me, that product there. All right, and then the second part is we'll come in with some sodium hydroxide, okay? Okay, so we pause, we think, we analyze, we look, right? So what do we have? So we have an alcohol here, okay? We're bringing in a strong base, okay? And we have a secondary leaving group there, all right? And so at the end of the day, we do have some competition for some different stuff that happens in this reaction. However, right, here is going to be what happens to get to our epoxide. Right? So we bring in our strong base. Remember, the sodium's a spectator ion, right? Acid-base reaction happens, okay? So let's see what happens after this first part. Okay, so we just do a transfer, right? Hydroxide into an alkoxide there. We remember about pKa's and equilibriums and all this kind of stuff, right? It's all happening. I promise it's there behind the scenes, okay? Now what, right? So now what do we have? Well, we've got a good nucleophile, a strong base, and it's next door to a good leaving group. A good leaving group, secondary, maybe not the best situation there, but what happens is this, right? So I'm going to show you guys a mechanism which you've never seen before. A nucleophile, let me pick a different color here. Here's a mechanism that you guys have never seen before. A nucleophile hits the carbon that is attached to a leaving group. I'm joking, by the way, right? This is a mechanism that you guys should have seen a million times at this point, okay? Because what am I showing you here? A nucleophile hits the carbon and makes a leaving group leave, right? What is that? That is an SN2, right? This is essentially an SN2, okay? And I say essentially because I really mean it is. So we have something attacking the carbon and making a leaving group leave. That's SN2, okay? Now the tricky part might be just understanding how and when and where and why. And the simple answer is this, right? This, and I really am simplifying this. I almost hesitate to kind of put some of this stuff onto video, because I know there's going to be somebody who's going to watch this eventually, and they say, well, you know, in reality it does this, right? And they're hammering away and they cite references and all this kind of stuff. Simplification, okay? If we want to sit here and argue the minutia, I'd be happy to. However, at the end of the day, right, we have a reaction that happens within one molecule, right? So this is an intramolecular reaction, right? Intra versus inter. And so if we stop and we think about this for just a second, okay? Intramolecular reactions tend to be the faster reactions that happen, right? They're kinetically favored, might be the fancy sounding $5 way of saying that, okay? Because we have to go back and think about how a reaction happens. We are doing chemistry on paper, okay? Chemistry on paper always works as long as we follow the rules that make chemistry happen, right? Here's what I mean. Here's what I mean by it always works. I drew this hydroxide here, and I drew this hydroxide attacking that hydrogen. It works. In reality, for that to happen, we have to have this molecule floating around in solution, and we have to have this molecule floating around in solution. Then these two molecules have to come together at the right speed, at the right angle, at the right time, and with the right vectors, with everything has to come together for this lone pair, or a lone pair, to overlap the orbital with this hydrogen that can then break the orbital to that oxygen and set up this system here, okay? So what I'm saying is a lot of stuff has to happen at the right time, at the right space, at the right speed, right, for that to happen. That's what I mean. But on paper, it's easy. We just draw it, we draw arrows, okay? So in reality, right, if we do an intramolecular reaction, right, these things don't have to find each other in space. They're already next door to each other, right? That's pretty darn easy, okay? If we want to go to a bad example, right, intramolecular reactions are like cheating on the person next to you on the exam. All you got to do is look over there, right? Intermolecular reactions is it'd be like you getting up, walking to the other side of the room inconspicuously, and then looking on somebody else's paper, right? At the end of the day, right, it's you know, one of those is just easier than the other one is. You get? I hope you understand what I mean, right? So intramolecular reaction here leading to our product, all right? So let's just wrap that up then, okay? Sorry, I had something on my screen. So we'll do this, right? Pardon my not so great artwork. Okay. Boy, that is just fantastic artwork. So these are two wedge bonds here, right? So this is going to attack, remember it's an SN2, right? This oxygen comes in on the opposite side of the leaving group, okay? This reaction can't happen if these are cis to each other, okay? So if they're on the same plane, then this can't happen, okay? But fortunately, right, when we do this reaction, they always come in anti to each other there, okay? But cool, there's another way to make an epoxide. Why would I do this way versus this way here? The answer is, it depends on what particular steps you need to do to get to your product, okay? And like I mentioned, MCPBA can react with other things also, amines in particular is what's coming to mind, okay? Right? And then, so if we have another functional group that might react with MCPBA, we might have to go through this route here to make an epoxide, okay? So remember, we're going to start thinking about multiple functional groups present in a single molecule here. Sound good? So there's our two methods that we have of making an epoxide, okay? A couple of quick comments about things here then, okay? So let's think here for just a second. Let's say that we have a cis versus a trans alkene, right? And we're just going to McPub it up here. All right. So cis and trans, and we're going to turn those into an epoxide. So here's our product, right? What happens in this case is if we, right, I'll draw my epoxide there, right? Okay. Those are technically the two products that I make. Now, for those of you guys that are observing, you go, wait a minute, right? Those are the exact same. You're right. I'm just making the point as an example here, okay? And down here, right? We get that. Now, the question is, are these the same, right? So stop and take a look, right? See if I drew the same or the different products in these cases. And that's always just a good opportunity for me to grab a drink of water there before I get a little bit parched, okay? This is important. You're gonna make a set of enantiomers when you come through and you make epoxides. This isn't too surprising, okay? In fact, if you go back and you think about it, with your alkene reactions, you pretty much always end up making a set of a set of enantiomers, if that is a potential, right? And because what I mean is this, right? These are, remember, alkenes are planar molecules, right? So the incoming MCPBA can attack from either side of that alkene. It can attack from the top and you make one enantiomer, right? And you attack from the other side and you make the other enantiomer. Very similar to what we talked about with carbocations, right? Because of their planar nature, right? We can add our nucleophile to the top or the bottom. Same thing's going to happen here with the alkenes. So pay attention to the starting geometry of the alkenes, if it's cis or trans, or E or Z, right? Then we're going to end up retaining that. We're going to end up retaining that orientation once we finish up with our product there. Okay. So just pay attention to that, and there's some fantastic drawings for you guys in the book that kind of cover this in a little bit more detail in case you forgot what cis and trans and E and Z and that stuff is. All right? Excellent, excellent. All right. So one thing then what we want to talk about is why in the world would we want to mess with epoxides? Well, they're actually pretty useful building blocks for us, right? We can do some very useful things if we bring in our buddy Mr. Epoxide here, okay? But before we do that, let's go and think, right? Let's say that we have this guy here, right? And we want to turn that into an epoxide. Yeah, you know what? We'll just go and do this, right? There's our wedged bonds, right? Okay, so MCPBA. Okay, so start with an alkene, turn it into an epoxide, and then let's do something with it. If I take my epoxide and I throw in some sodium hydroxide, okay? So I take my epoxide, throw in some sodium hydroxide with some water, right? Just to make sure that's kind of around. Okay. Let me do this. Pardon me for a moment. Let's bring that in blue. Just for argument's sake there, okay? So NaOH. So again, the first thing to do is stop, think, and look, right? So strong base, good nucleophile, right? Polar protic solvents, epoxide, ring strain, and we talked about ring opening, okay? So what we're gonna learn is there's two ways that we can open a ring in general, right? We have acidic conditions and we have basic conditions, all right? So we have acidic and basic conditions that we can use to open an epoxide ring. We'll talk about the base first, all right? So we are under basic conditions, right? How do we know and how do I recognize all that kind of stuff? Hopefully you guys are with me on that. Sodium hydroxide, a strong base, okay? Here's what happens. The sodium there, right? That's just a spectator ion. It's just doing its thing, okay? Watch. So watch the arrows I'm going to draw, and then I'm going to ask you guys a question about it. And I'm going to immediately answer it because I'm basically speaking to myself like a weirdo. Okay. What do those arrows tell you? Right? Let me zoom in here for just a second. Okay. So what do those arrows tell you? What do they show? What mechanism does it look like? What product, was the stereochemistry going to be at the end of this? All these kind of very important questions with that, right? So pause, take a look at it, see if you can answer what mechanism that looks like, what's the product going to be, all these kind of things, right? So if you're with me, right, we have a nucleophile attacking a carbon and essentially kicking off another group, right? So we have a group that is leaving, okay? So this is very much like an SN2 reaction, okay? So my product then, right, is going to look like this. we've got the sodium around, and it'll pick up a hydrogen in just a second, okay? But what does this tell you? So now we have, the incoming alcohol group is on the opposite side of where the other oxygen is, right? So we're going to have a trans configuration here, right? Let's just finish this up by protonating. Okay, let's protonate this alkoxide there. So we'll grab a hydrogen from the solvent, right, from the solvent water, and then we will call it Dunzo for that. Cool. Okay. Fantastic. We end up generating a hydroxide at the end, right, which can go back and continue to react with this. Okay? So under basic conditions, we follow, right, here's the important thing, under basic conditions, we follow SN2-like mechanisms. Okay? Stop. What does that immediately tell you? Okay? So here's one of the important things. If you remember, if you had watched the last lecture already, I told you guys that remembering the key parts of OChem 1 is going to help you out in OChem 2. And so when you think SN2 reactions, really the first thing that pops to mind should be sterics. Okay? And if we're following an SN2 type mechanism here, we're going to be following the rules of sterics, which means, right, the incoming group is going to hit the less substituted side of an epoxide. Okay? So if we drastically change things up, okay, let's skip a step here. Let's just go right to our buddy, Mr. Epoxide. My goodness, I can't draw all of a sudden. All right. I don't know why I'm struggling with my drawings today. I really apologize, guys, but I'm not an artist, but there we go anyway, right? So we have an epoxide, and, right, one side of that epoxide has this methyl group, right, with the epoxide here, right, the other side doesn't. So we have an asymmetric, right, we have an asymmetric epoxide ring there, okay? If we put this under the same conditions as we did before, right, so let's bring in some NaOH and some H2O, okay? So pause, see if you guys can come up with a product for this then, okay? What's my product going to be after I follow through with this reaction? So remember, we're following SN2. SN2 has to deal with sterics. The incoming nucleophile is going to hit the less sterically hindered side. And so at the end of the day, right, at the end of the day, that's what my product's going to be, okay? Neat. So now we have a way of making transvicinal, next door to each other, right? Transvicinal diols, okay? So transvicinal diol. So base opening, right? Opening an epoxide ring under basic conditions. That's how it works. The incoming nucleophile hits the less substituted side, okay? Any good base can make this happen, right? So we can have alkoxides, right? So instead of just hydroxide, we could bring in F oxide or something like that, okay? Sodium cyanide, that's going to be pretty important, right? We're going to do a lot of cyanochemistry a little bit later on. We can bring in Grignards, okay? Very nice. We'll talk about this here in just a second, why that's important. And even, okay, we could bring in something called LAH, okay? So I'm looking at a list of reactions on page 576 here, okay? So take a look at page 576 and you can kind of see where I'm kind of pulling these from. Is this a comprehensive list of anything that you can bring in? The answer is, of course not, right? Of course not. But why I do like this, right, is because we have some very useful different functional groups we can bring in there, right? So let's very quickly kind of point these out, okay, in generic terms here, right? and just kind of see what happens. So there's about as simple as an epoxide as you can get. Let's bring in each one of these here and kind of see what happens, okay? So first things first, let's bring in, and you know what? We'll just go ahead and give a definite example then, right? So we'll bring in some O minus, right? We'll bring in an F oxide in ethanol, right? F oxide in ethanol. And my product here is, after we're all said and done, right? After we're all said and done, we end up making this, okay? Pause and go, right? What did I end up making, right? Well, we ended up making an alcohol. That's the same as what happened, you know, up there. But what functional group did we end up making here? Well, that's another ether, okay? So now, right now we have another method of making an ether starting from an epoxide. And we have an alcohol left over. What can we do with alcohols? The answer is a lot, right? We know a lot of reactions that can deal with alcohols, and so we're good to go, right? Let's, we'll stick with the same starting material there, right? But now we'll add sodium cyanide into it, right? So I'm just bringing my epoxide down. So again, if we do this in water, right? Perfect, we have a good nucleophile, right? It's gonna come in, right? Hit the less substituted side, right? Hit the less substituted side, add a cyano group there. Why do we care? Well, we'll talk more about cyano groups a little bit later. Let's talk about LAH here real quick. Let's do this, well, let's switch that out to, you know, a different color. All right, so LAH. Let me give you the product here, or let me give you the conditions, right? So we want LAH, and we want, you know, usually water. You can also technically finish this out with acid also if you wanted to. Doesn't matter. If we do this here, is my product. Awesome. What did I do? Well, LAH, and I'll tell you what it is in just a second, we add a hydrogen, and we end up making an alcohol. So let's see if we can back this out real quick here, right? So what does this mean? This is the hydrogen that got added from LAH. So what does that mean about that hydrogen? That hydrogen has to be a good nucleophile, okay? That incoming hydrogen had to be a good nucleophile. And it had to be a, you know, which means it had to have a negative charge on it, right? So we brought in a hydrogen with a negative charge. That's our good old buddy, a hydride, right? We talked about hydrides last time. So LAH stands for lithium, aluminum, hydride. So LiAlH4. Okay, that's what that is, lithium aluminum hydride. We're going to see this guy over and over and over and over and over again, right? It's a very good reducing agent, right? That means it's good at adding adding hydrogens, removing bonds to oxygen might be another way of thinking that, okay? A very powerful reducing agent that is a hydride, which means it has H minuses that it brings into the system, okay? Awesome, LAH. And then finally, and certainly not least important, is let's bring in a Grignard. Let's bring in generic Grignard, MGBR. And we'll finish this up with some water also, okay? So what do we remember about Grignards, or what did we learn about those? Well, remember the MGBR stuff is just a placeholder, is what I always share with my class when I introduce this, right? This is a positive charge. That means whatever it's bound to has a negative charge. So a Grignard is a carbon with a lone pair and a negative charge, okay? So my product here, after it's all said and done, let's do this in red here, right? Just so we can kind of draw the point here, right? So there are my two carbons that get attached, right? So we bring in two carbons to hit that carbon there, right? And then we do a ring opening, okay? So let me pause and just make a couple of quick comments here, okay? First quick comment, count your carbons. I almost made a mistake when I was introducing this to you guys right here, right? Because I was like, oh, okay, how many, right? It's very easy to lose track of carbons. right? It's very easy to lose track of carbons. Do yourself a favor, number them, dot them, whatever you need to do, double check, triple check, right? You're bringing in 2 carbons, so you better have 2 carbons here that attack that carbon that is right there, right? So we have 1, 2, 3, 4 total carbons, 1, 2, 3, 4 total carbons. Thumbs up, okay? Do yourself a favor, right? Check once, check twice, that way you don't have to cry after the exam, okay? What is useful about this? Here's the very cool thing. In all these other cases, right, we had, you know, or there's an exception I'll talk about in a second, right? What's useful about this is now we can make another carbon-carbon bond. Those are extremely useful reactions, okay? Carbon-carbon bonds are useful to bringing larger molecules together to make something new, okay? So we make a carbon-carbon bond if we put a Grignard in with an epoxide. So if we have 2 molecules, one with an epoxide, we make some generic, you know, we make some Grignard here, we can bring those 2 together, we can do a sort of coupling reaction there, okay? Now for those of you guys who are observing, you say, that's not that impressive, Dr. H, we already made a carbon-carbon bond. And you're right, the cyano group here, right, we have a carbon there, that does make a carbon-carbon bond. So if you were observant with that, you're absolutely correct. But always pay attention to making those carbon-carbon bonds, okay? All right, I think this is a good stopping point. This is ring opening under basic conditions. Next time we'll come in and we'll do ring openings under acidic conditions. All right, I'll see you guys next time.